Good morning, everybody. I hope you guys are doing well today. All right, the Olympics have started. Woohoo! So, um, can probably find me in front of the TV in the evening hours watching those. Um, Big fan of the Olympics over here, right? So it's amazing how fast the evening hours go when I'm just sitting in front of the TV watching skiing or snowboarding, and stuff like that. Not a fan, Isaias? Oh man. My kids aren't so much either, but that's all that's on my TV for the next couple weeks here. It is, right? When they give like a 17-year-old winning a gold medal, or even when they like talk about how like a 34-year-old is really old, and I'm like, oh man, that's my age. So imagine how I feel when they say like a 34-year-old is like a dinosaur in the sport. I'm like, ah, I missed my prime. I guess I won't be going to the Olympics anytime soon. At least not as an athlete, I guess we can say. But still fun nonetheless to watch and root for Team USA and everybody else. So I have very strong roots in the Netherlands, by the way. So we cheer a lot for the Dutch in our household as well. All right, but back to our pre-calculus. All right, so were there any major questions with your polar graphs? So as I was going through things and that 6.05 lesson, everything looks really, really good. You guys got your polar graphs coming out correctly. We saw that nice rose curve, I think it was in question one. So you guys got that to graph okay. Um, Maybe just a minor, like, error along the way with one of the questions here or there, but nothing that glaringly caught my eye that we need to kind of reteach as far as 6.05 goes. So I think we're safe to go into 6.06. And I listened to it this morning, but I get it wrong every time on how to say this person's name. Demore, something like that. I had to even listen to it on Google, the pronunciation. But this guy's theorem and the nth roots are what we're going to be looking at today. So, Demore, something like that is how you say it. And I know I'm probably saying it completely wrong, still to this point, even after I've listened to the pronunciation of it many times this morning. But essentially, what that means is we're going to be looking at the complex plane. So that complex plane is really not going to be too bad. All right. You guys are arguing about your Olympics still. I'm assuming we're good to go into that complex plane. All right, let's venture forward. All right, so the complex plane is going to seem very familiar to you. It is much like your um, coordinate plane that we're used to, except we have a real axis and an imaginary axis. So your x-axis is going to act as your real axis, and that y-axis that we're used to is now going to be related to our imaginary axis. So when we're dealing with these complex numbers, remember you have a real and imaginary part, a plus bi. So this is nothing new. We learned this all the way back in Algebra 2 already, what complex numbers were. So the real part always comes first, that's the A, and that imaginary part always comes second, that's your BI, right? So as we go to graph these, we almost think of them as an ordered pair. So A is going to be the x coordinate, so to speak, and B is going to be that y coordinate, so to speak, that we're used to. So let's go ahead down here, and we're going to go ahead and plot these three complex numbers. And yes, there are three because we do have to find that third complex number by adding the first two together, but that is nothing complex, haha, no pun intended. It's really just adding your like terms to find that third set. So the first one, 1 plus 3i, what ordered pair does that remind you of? So 1 plus 3i. If I were to tell you to graph that, what ordered pair would that remind you of? Don't overthink it. If you were to pull an xy coordinate, all I want is an ordered pair for 1 plus 3i. So an ordered pair that comes to mind should be 1, 3, right? You got the real number of 1 and positive 3 for that imaginary number. So when we pull that to graph it, you should just think of the point 1 comma 3. And that's how it's going to be graphed on your complex plane as well. So you go 1 over in the real part and 3 up in the imaginary, because it is a plus 3i. When you see the second number, 2 minus I, what point does that remind you of? So what ordered pair does that remind you of? There we go. Yep, 2 negative 1, right? So, and I'm going to go ahead and label these. So 2 negative 1 reminds me of that point right there, because we go 2 over on the real axis and 1 down on the imaginary. And then the last piece is the u plus v. Well, we have to figure out what that complex number is first before we can graph it. So if I'm adding these two together, what is that going to result in? So first of all, let's add the two complex numbers together. What do we get when we add those complex numbers together? A 3 plus 2i. Once we have that, we can then graph it on our complex plane. Should remind you of the ordered pair 3, 2, right? So we'll go 3 to the right on the real axis, 2 up on that imaginary. All right, now it says these 3 points and the origin. So I'm going to go ahead and take that origin into consideration as well there. Determine a quadrilateral. So if I were to connect all these points, they are in fact making a quadrilateral here. Is that quadrilateral a parallelogram? Well, what do we actually want to test? We're not going to go through it all here today because of time, but what would we do to test and see if that shape is actually a parallelogram? Do you guys remember the properties we're going to test and look for from our geometry days? First of all, the opposite sides need to be parallel, right? So we can test for the slope of these sides. Yep. So you can go ahead and look for the slopes of those in bluish there and make sure that they are the same. And you can do the same for the pink. So if you're going to find just the slopes, we do need to compare the opposite sides, and both of those slopes must be equal, right? So the blue slopes must be the same and the pink slopes must be the same, because that means they're parallel lines. Or there's another approach you can take. You can look at just one set of slopes, and then if we looked at just one set of slopes, what other data would be needed? So let's say we were just going to focus on those blue slopes. What other piece of information would we technically need to find to show that that would be a parallelogram? If the lines are the same length. Exactly. So you would actually have to use your distance formula, and use the points there from the origin and U and find the length of that blue line, and do the same thing from V to U plus V. So there's a couple different approaches you can take to prove that that's a parallelogram. I think the most common one and the quickest one maybe for us might just be looking at the opposite pairs of slopes, right? So just finding the slopes of those two pieces or those two sets of parallel lines. But some of us favor the distance formula over the slope formula. So if that's the case, you can use the distance formula to find the lengths instead. We're not going to do that, obviously, like I said, for time's sake, but this does come out to be a parallelogram. So if we were to compare the slopes and the distances, it would actually show us that that is a parallelogram. All right, any questions with how we graphed those? And then how we could go about proving that the shape actually is a parallelogram once it is graphed. So we're keeping it kind of basic to start things off here with our complex plane. All right, let's kick it up a notch, right? So we kept it basic, related that back to something we were familiar with the ordered pairs and our parallelogram information. The next thing we're going to talk about is the absolute value or modulus of a complex number. When you take a look at this, it says the absolute value or modulus of a complex number, z equals a plus bi, is found by performing the square root of a squared plus b squared. What does that remind you of? So what does this formula remind you of here? It should be familiar formula. Hopefully. Fingers crossed. Magnitude! Yeah! It should remind you of the magnitude because that's essentially what your modulus is asking you to find. It's asking you to find that length of that point, that complex number from the origin. So that really should remind you of the magnitude because that's exactly what you're trying to find here. It's the distance from that point is from the origin. So when we look down below here, we can go ahead and see this complex number out here, a plus bi, and then we're trying to find that length from the origin. So in blue here, that is going to be that magnitude. So we can relate this all back to our vectors, so to speak. And we can also relate this back to the trigonometric form or the polar form that we just got done speaking about in terms of A equaling the r cosine theta, which is this piece right down here, and B referencing the r sine theta, which is this distance right in here. So if we relate this back to our trigonometric form with our unit circle, we can go ahead and find those lengths using r cosine theta and r sine theta. Okay, so essentially what this is going to allow us to do is take this complex number and we can go ahead and find the trigonometric form of that using cosine and sine. So right here we're going to go, we'll see, I think we're going to see this on the next slide, but I just want to point it out right here. This is your complex number in the trigonometric form. You're going to take r times cosine theta plus I sine theta. So essentially what they did there is they replaced the a with the r cosine theta, replaced the b with the r sine theta, and they factored out the r that they had in common. Right, so that's how they got to that trigonometric form of z below. Yep, and here it is. I thought I had it on the next slide here, but here's that trigonometric form of a complex number. We will go back and forth between your complex number and the trigonometric form throughout this lesson. So having this handy is going to be key to our success. Again, we probably want to realize that oopsie, and that's green is not the easiest to see here, so let's change the color. We have these individual pieces here that help us make up that trigonometric form. So A again is that r cosine theta. B is that r sine theta. If you're dealing with just the trigonometric or the complex number itself, you can go ahead and find r by using that magnitude formula, right? So we essentially can find r in that form with just using the complex number alone. And same thing with theta. If we needed to, we could go ahead and find theta of our complex or trigonometric form there by using tangent theta equals b over a. So essentially we would take b and a from that complex number, and we want to use tangent inverse of that to find the actual theta. Okay, so lots of little pieces there, but the good news is that none of it is brand new to us. We've seen these bits and pieces before in our previous lessons. Let's see. Oh, theta is just an argument of z, meaning, did I have that on the previous slide? It is just in relation to z. Let's see if we have that formal definition in our book here, because that's a vocabulary term. I think when it says argument, it just means that it's of the form, the trigonometric form right here. So when it says it's an argument of z, I think it just means that it is in the trigonometric form. Yeah, so it's relating back to that trigonometric form. Now, I do want to point out that because we're dealing with trigonometric forms here, that our answers are not necessarily unique, right? We can go around the unit circle multiple times and still land at that same spot. So our answers that we get are not necessarily unique here. We can get multiple representations of that point. All right, let's go ahead and take a look at the example below it. Use an algebraic method to find the trigonometric form from 0 to 2 pi. So that's going to be important as well. They are narrowing our search here, and we're just looking in that unit circle area that we are familiar with. It says approximate answers with a calculator when appropriate. So to change it to this trigonometric form, we need r and theta. So let's start by finding r. So to find r, remember we use the square root of a squared plus b squared. So a squared in example A here is just 1. And what is going to be b squared? Yeah, just the 3, right? Because the square root of a squared is just that number underneath. Or the squared of a square root, I should say, is that number there. So we're looking at the square root of 4 here, which is just our 2 for r. All right, next let's go ahead and work on finding theta. Now theta, we have to be careful of what we're looking at here. Because we do want to make sure we're grabbing the correct theta based on the quadrant that we are falling in. So we'll go ahead and take a look at the setup here on how to find theta first. So tangent inverse of b, which is negative square root 3, over a, which is 1. First of all, what quadrant does this complex number fall into? So if I'm looking at 1 minus square root 3i, what quadrant would you expect that to fall into? All right, we're looking for what quadrant 1 minus square root 3i is going to fall into. Is that going to fall into quadrant 1, quadrant 2, 3, or 4 on that complex plane? So here's 1, 2, 3, and 4. So positive 1, negative square root 3 is going to fall in quadrant 4. So as I'm searching for theta, thanks Isaiah, as I'm searching for theta, I need to make sure I'm looking in quadrant 4 for this relationship right here. Where does tangent equal negative square root 3 over 1 in quadrant 4? So specifically in quadrant 4, that narrows down your search quite a bit. So where does tangent equal negative square root 3 in quadrant 4? Tommy says 5 pi over 3. I would agree. 5 pi over 3 is your sine over cosine, right, for your tangent values, and that's going to give you the negative square root 3 over 1 once you're done simplifying that. All right, so now that we know what r and theta equal for this first complex number, we can go ahead and finally put this in the trigonometric form. So we'll go ahead and say r times cosine of our theta plus I sine of our theta, which was our 5 pi over 3. If we wanted to, we could go ahead and distribute that 2, but we'll go ahead and just leave it like this, seeing how that's how they have z represented up above. Okay, questions with that first example before we take a look at part B? Okay, part B, we're going to follow the same guidelines there. So we have to start by finding r. Oopsie. So remember, r is found by taking the square root of a squared plus b squared. So in this case, what is our r value in part B? A 5, thank you. And then we can find theta by doing tangent inverse of b over a. All right, now this is going to be a little bit more complicated because 4 over 3 is not values from our unit circle, right? So we're going to have to probably do a little bit of work behind this to find the correct value for theta. First of all, we have to identify what quadrant our complex number falls into. So taking a look at -3, -4, what quadrant in our complex plane does that fall into? That falls into quadrant 3, right? It's somewhere down over here in green. So we know that our theta has got to fall into quadrant 3. All right, let's use our calculator, and we're in radian mode right now because we are looking from 0 to 2 pi. So let's go ahead and get that decimal value for theta. So again, make sure you're in the radian mode and not degrees because we are used to working in degree mode. And let's do our tangent inverse of 4/3. Should be 0.927. That's what I get as well. Now, when we think about that algebraically and we relate that back to the unit circle, remember this is 0 and we have pi over here. Well, pi is 3.14, right? And pi over 2 is 1.57. So our 0.927 is probably falling somewhere right out here. I want to make sure that we're falling out in quadrant 3. So to get that actual representation in quadrant 3, we're going to add pi to that, right? So essentially we probably want to go halfway around to get to that correct spot. So let's go ahead and take this 0.927 because right now that's falling in quadrant 1, but we want our answer to fall in quadrant 3. So we're going to go ahead and add pi to that to get that reference angle there. And what decimal does that put us at approximately? So 4.07. That's what we're actually going to use for our theta there. So we do have to do a little bit of work behind that, and note that we've got to add pi to get to the correct spot for that theta in our coordinate plane there. But now that we have that correct value for theta, we can use it in that trigonometric form. So we'll go ahead and do 5 times the cosine of theta. It just looks a little bit weird because we're using a decimal answer here versus like your radicals. But it still comes out the exact same. So this is how we can express it in that trigonometric form. So a little bit more challenging with that second example there because we did have to find the correct value for theta using our knowledge of the unit circle and knowing what quadrant we wanted our theta to fall into. Questions with that second example at all? All right, then once we have our complex numbers into that trigonometric form, we can multiply and divide those. So multiplying, we're going to go ahead and multiply the r values out in front of those trigonometric numbers. So we multiply those together, but the thetas we're actually adding. So when we look inside here, we're adding the thetas together. When we're dividing our complex numbers in the trigonometric form, we do divide the r's out front. But you may have been able to guess this. We're going to subtract the thetas inside. Right. So we're going to kind of keep it basic. Remember, when you multiply, you add the thetas. When you divide, you subtract the thetas. So let's start with, I believe we're trying to find the product of these two trigonometric numbers, right? So we're going to go ahead, if we're finding the product, that means we're going to multiply the r's out in front to start us off. What is 25 square root 2 times 14? And again, we'll go ahead and actually leave this as an exact answer. We'll leave the square root of 2 there. So essentially we're looking for 25 times 14. Yeah, so 350 square root 2. It's kind of hard to see. I apologize. That bright green is hurting my eyes here this morning. And then inside, we're going to go ahead and do we add or subtract our thetas? We're going to add them, right? Because if we're multiplying, we add. I got to switch out. That's way too bright for me. All right, in order to add the thetas together, what do we need? So you're dealing with basically two fractions here. In order to add two fractions together, you must have a common denominator. In this case, the common denominator is going to be 12, right? So if I multiply my first fraction by 3, that'll give me a negative 3 pi up in that numerator. And if I multiply that second fraction by 4, what is going to be that theta inside of my trigonometric value here now? Negative 3 pi plus 4 pi. It's just a 1 pi, right? Or a pi over 12. So as I go to write this final answer, or the product of these two trigonometric numbers here, we'll start with the 350 square root 2 on the outside, and I'll end up with cosine pi over 12 plus I sine of pi over 12. Sometimes we can leave our answer just like this. Other times they'll actually turn it into decimal values. If you want to turn it into decimal values, you'll have to do cosine of pi over 12 and sine of pi over 12 and see what those convert to, and then multiply through by that 350 square root 2. So sometimes you'll actually see that written as decimal answers, and if that's the case, it would convert to about a 478.11 plus 128.11i. So depending on how they want you to write your answer, I believe it does say in standard form. So if it does stay in standard form, we probably should change these to decimals and distribute the 350 times square root 2 through those. And this is your standard form. The a plus bi is what they're referring to as your standard form. So the real number first and the imaginary number second. All right, any questions with how we did that? All right, then let's go ahead and take a look at dividing a complex number. So when we're dividing, it's just what you would think. We're going to go ahead and divide the r's out in front. So 2 square root 2 over 6. That is going to simplify. I believe that's going to simplify to a square root 2 over 3. Right? And then if we're dividing, what are we going to do with our thetas inside? So 135 and 300, we're going to subtract them respectively. It looks like we're going to get a negative value here, if that's okay. What is 135 minus 300? a negative 165. Our calculators can handle that. Not a big deal. If you wanted to get the positive representation of that, you could. But because we need to put this in standard form, we're going to have to change this to a decimal answer anyway, and it's going to come out just fine. So again, let's go ahead and make sure we distribute this square root 2 over 3 to both of these values here. So let's start with the square root 2 over 3 times cosine of negative 165. What do we get when we multiply those together? And again, we're working in degree mode, right? So make sure you switch that calculator over to degrees to get the correct decimal value. What do you guys get approximately for that decimal when you're multiplying through just by the cosine? We'll start with just this cosine piece first. A negative, good. So I just want to make sure everybody was able to get that value in their calculator appropriately. Looks good. And then let's do the same thing with the sign. So we do need to distribute that square root 2 over 3 there as well. So what do we get for the sign value? A negative 0.122. I'll see if anybody's going to second that. Yep, Isaias is going to second that, and Rachel also is going to third that. Okay, now don't forget, I'm going to put the I here because we need that for that standard form. That imaginary part has to be put into place, so we need that I after it. But that is the standard form for the quotient of these two complex numbers. So not too bad, right? As long as we can remember to switch our modes accordingly, I think that's going to be the key piece in this, is making sure we're working in the correct mode for radian versus degrees. I'm just paying attention to the detail. All right, a couple more concepts to look at today. Any questions with that? I'm not sure if we would get the same output. We could try. You could try changing those to your standard forms and then seeing what you get. I'm not quite sure if it would come out the same or not. But it's worth a shot to give it a try. Maybe after class you can give that a go and see if it comes out. Yeah, in your free time, right? And let us know, report back to us if it does or not. All right, the next thing is de Moivre, again, probably saying his theorem wrong, so I apologize. But basically what de Moivre's theorem says is that we can go ahead and find the trigonometric form here of a power. So what we have to do to find this form if we're given an exponent on the outside, and it's actually pretty slick to change this from standard form to our trigonometric form, we are going to find r first of all. So that's the first step, is finding r. And finding r is the exact same way that we would any other time. So if it's 1 plus square root 3i, we would take a squared plus b squared. So in this case, that b squared is just a 3. So we're looking at our r value of 2, right? And then the next thing we have to do is find our theta. So theta, remember, is tangent inverse of square root 3 over 1. And we are looking at this complex number in quadrant 1, right? So where does tangent equal square root 3 in quadrant 1? At pi over 3. Okay, believe it or not, the hard part is done now, because now to find that power, we're going to take r to that power, so 2 cubed, right, because the power on this was 3. And then we're going to go ahead and inside, we're going to multiply by that power. So theta times that power of 3. So on the outside, that turns into an 8. And theta inside looks like that's going to simplify down to just a pi. Okay, so De Moivre, or whoever you say his name, his theorem's actually pretty slick here. And now we can translate this still further. What is cosine of pi? And what is sine of pi? So using our unit circle real fast, and maybe we even have this point memorized. What is cosine of pi and sine of pi? So -1 and 0 respectively, right? So really what I'm looking at here is just a -1 inside, and when I multiply that together, we end up all the way down with a -8. Oops, and I meant to put an I, not a pi here. So my bad. That was supposed to be an I, not a pi. All right, so we simplified that all the way down to a -8. Questions with how we applied his theorem there to get that -8? It's pretty slick, and most of the time we will get it down to just an integer value at the end. And I'm going through this kind of fast, I apologize, because there's one last topic that I want to talk about, and that is finding your nth roots of a complex number. So here, if I have, find the 4th roots of this complex number, we always start with our k equaling 0 first, and we kind of follow this format. So if I'm finding the 4th roots, I'm going to begin with k equaling 0. All right, and then I'm going to find k equaling 1, k equaling 2, and k equaling 3. So essentially, in the 4th roots, we should have 4 answers to this problem, right? But we always start with k equaling 0 first, and then we finish with that n-1 value. So since we're finding 4 answers, or the 4th root, we end at 4 minus 1, which is that 3 value for your k. Now, to start us off, since we're finding the 4th root, we do the 4th root of that r value of 5. Okay, so otherwise that's also known as 5 to the 1/4 power, right? So if we need to calculate that at some point on our calculator, remember we can convert that to a rational exponent of a 1/4 power if needed. All right, inside, we're going to follow our formula set up above. So we're going to start with cosine of theta, which in our case is pi over 3, plus, then we can insert the value in for k. Well, since our first value for k is 0, we just add 0 at the end here. And n is your root. So in our case, n is going to be 4 because we're finding the 4th root. All right, we do want to simplify what we're going to get in here. And I just like to put a ... because the sign is going to follow the exact same value that the cosine will take on. So once we simplify inside there, that's going to be a cosine I believe, of pi over 12. Okay, any questions with how we did that first root? So here's the first answer out of the 4. Then we just follow the same format for the remaining 3. And you'll probably notice a pattern establishing once we get the hang of this, because there is going to be a pattern. This time, k is 1, so we're going to be adding a 2 pi in our numerator. Once that simplifies, and you will have to do a little bit of algebra on the side to get that to simplify, you'd want to add the numerators together first with that common denominator and then divide. But that is going to simplify down to a 7 pi over 12. And then I'll keep going for the last 2. So I know I'm going through it a little bit fast, but again, we're just using our pattern here. Because k is 2, technically we're adding a 4 pi on in the numerator now. And then you can probably guess in the last one we're adding a 6 pi. So that's going to simplify down to a 13 pi, because if you didn't notice already, we're adding 6 in that numerator each time. So you will notice a pattern there as well. There should be one established after a couple roots. I think the hardest part from here on out now is just writing the answer. It takes so long to do that. Adding another 6 I think is going to give us a 19 pi. That's going to simplify too. And again, all of that simplification you can do off to the side for this piece right in here. So I know I went through that fast, but that can all be handled off to the side using your algebra facts and how we can add and divide with our fractions. All right, phew. But we got the 4 answers there, and that was the key thing, knowing that we're finding the 4th root. There are 4 answers that we should have for our answer. All right, questions with that process at all? So it's all about finding those patterns within there to kind of speed the process up a bit. All right, we got through everything that I needed to. We just didn't get through some of those practice ones, which is okay. Just make sure you're kind of practicing on your own there before you get to that homework assignment. But you should be good to go. You have all the topics you need to attempt that homework assignment now for 6.06. I do believe that this was the last lesson, I want to say, of the chapter. So from here on out, I think we're just going to be reviewing on Thursday's class for the test. And then we'll venture into Unit 7, which is on our matrices next. So a nice change of pace in Unit 7. We focus a lot on algebra in that next unit. So something to look forward to. All right, if there are no other questions, I'll let you guys go for the rest of the day. Have a great day, and I'll see you again Thursday morning. Bye, everyone.